A chi-square tests the null hypothesis that category frequencies, or proportions, arise by chance, and that there are no real differences across categories. Now there are several steps to take in calculating the one-way chi-square. Step 1. Specify the hypotheses. So in the example above, in which we're examining whether packaging design influences purchasing decisions of teenagers, the null hypothesis is that both frequencies or proportions are similar. So in other words, the probability or the proportion of getting absolute bore is equal to the probability of getting absolute colour, which is equal to the probability of getting absolute excite. So the alternative hypothesis is that there is a difference between these proportions. So there is a difference in the number of bottles at each level of advertising, i.e. a real chance difference. In other words, the three proportions are not equal. So to do this, the chi-square compares the observed frequencies to the frequencies that we would expect by chance. So step 2 is specify the decision criteria. Now, as with any inferential statistic, if the difference between the two, the observed and the expected frequencies, is so large that the probability by chance alone is only 5 times in 100 or less, then we reject the null hypothesis and accept the alternative. That is, that there is a real difference in frequencies across the categories, and one that is unlikely to have occurred by chance alone. Of course, this assumes that we're using the conventional alpha level of 0.05 as our significance level. Now, if only chance is responsible for differences among categories, then there should be a good fit between the expected frequencies due to chance and the actual observed frequencies. The one-way chi-square, also known as a chi-square goodness of fit test, because it tests the goodness of fit between the observed and the expected frequencies. The null hypothesis tested is that there is a good fit. So if significant, we reject the null hypothesis and conclude the data does not fit the expected or chance frequencies. Step 3, calculating the one-way chi-squared. So we're going to test if the frequencies of bottles purchased differs as a function of the type of advertising. In this example, the number of bottles are the cases, and the frequencies of the cases of each type of alcohol packaging are shown here on the slide. Of course, we need to assume that the bottles are comparable in all relevant aspects. That is, that they have a comparable type of alcohol, so the same type of alcohol, same price, and so on. We also need to check on some assumptions. While the chi-square does not have the parametric assumption of normality, it does require the assumptions listed here. Observations fall in one and only one category. So it should not be possible for participants to be included in more than one category. In this example, people in the sample shouldn't buy 2 bottles from different categories. There's also the assumption of independence. There should not be any influence of buying one bottle on another bottle. For example, I have a friend who likes to buy different bottles because they look good on the shelf. In this case, one bottle is influencing the purchase of another type of bottle because they both look good together. People in this sample should not be influenced by other categories. The data is not interval or ratio level data, but rather frequencies. In this case, the number of bottles purchased in each category are frequencies. Let's say young people are observed buying 1 bottle of alcohol at the local bottle shop, and it was noticed what type of advertising was on each bottle. Now let's assume there are 3 different brands of alcohol when buying alcohol, and that is Absolute Snore, Absolute Colour and Absolute Excite. Let's also say that only chance is determining their choice. In other words, there's no real alcohol preferences. Approximately how many would you expect in each bottle, in each category? How many bottles of Absolute Snore? How many bottles of Absolute Colour? How many bottles of Absolute Excite? If across 300 bottles, only chance was determining your choice. If only chance was determining your choice, then you would expect a frequency of 100 bottles in each of those categories. So your expected frequencies are 100 bottles in each category. That's your expected number. It's not necessary for you to be able to calculate the chi-square by hand. However, it is good for you to know the nuts and bolts behind the scenes when SPSS calculates a chi-squared. It just helps you to understand what's going on. So here we are again looking at the data from the hypothetical study in which we're wanting to test whether alcohol packaging is related or it influences young people's buying decisions at the store. So how does this calculation go on? Well, you can see here that I've got a chi-square formula. It reads chi-square equals the sum of each observed minus expected frequency squared and then divided by the expected frequency. Now, to show how this is calculated step by step, the table at the bottom is useful. The first column of figures shows the observed frequency. In our example, this is the number of bottles that were purchased in each category. So as you can see, this sums to a total of 300 bottles purchased over the period. Now, if the purchases result from chance alone, then we would expect the total number of bottles bought across that period to be equally distributed across each of the different types of packaging. That is, a third in each type, what we calculated before. This is the expected proportion or the expected number. So the expected proportion is P. With a total of 300 bottles and our chance expectation of a third in each type, our expected frequency for each type of packaging is 100. This is the E value. Next, recall that the chi-squared compares the observed to expected frequencies. And this we can obtain by simply subtracting the expected E from the observed O. The only trouble is that we will always sum to 0 here, which is why our formula requires us to square each of the O minus E's. Now in the last column, we take each O minus E squared and divide it by E, and sum it across all of them to give us our value of chi-squared of 36.5. Now, as with any hand calculation, before we can look up probability tables or write up our results, we need information on how many categories are being compared. Knowing how many categories are being compared allows us to calculate the degrees of freedom. For a one-way chi-squared, the degrees of freedom is calculated as degrees of freedom equals to k minus 1, where k is the number of categories. In this example, there are 3 categories of packaging or advertising, so it's 3 minus 1, which is equal to 2. So with this information, we now know that the chi-squared has a degrees of freedom of 2. We can now go to any statistics book to see if our chi-square equals or exceeds the critical chi-squared for the degrees of freedom equal to 2 with an alpha of 0.05. If the observed chi-squared, also known as the calculated chi-squared, if it does exceed the critical chi-squared, then it's significant, and we reject the null hypothesis that the categories are really equal in the population and that the difference arose by chance alone. Instead, we conclude there are real differences in the purchase of bottles of alcohol across the different packaging styles. Of course, if not significant, we retain the null hypothesis that there is no real difference in the purchase of bottles of alcohol across the different advertising or packaging types. So to calculate the statistical and research conclusion, please go to the SPSS videos that are accompanied here. Please note that you need to have a good understanding of the SPSS output that is generated by a one-way chi-square.